So today's section, in the last unit in section C that we're going to go over, is L'Hopital's rule. So what we saw in the only learning outcome for this lesson is using L'Hopital's rule to evaluate a limit which is in an indeterminate form. And back in Unit B, when we started doing limits, we saw that there were several indeterminate forms. The most common one was 0 over 0, or some combination of infinity over infinity. And the only way we were able to get out of that was by doing some algebra manipulation on the equation, and then hopefully we were able to cancel something out or rewrite the equation in such a way that we got out of the indeterminate form. And then if we couldn't do any algebra manipulation to get out of it, we were stuck, and a lot of times had to conclude that the limit did not exist. So now what L'Hopital's rule does is it says, well, if we have a ratio of two expressions, and they are both differentiable on an open interval containing a. Now what we mean by that is if you're evaluating the limit to a specific value, the functions have to both be differentiable around that value. Then what we can do is we can say, well, if we get an indeterminate form from the original structure of the limit, we can take the derivative of the numerator separately from the derivative of the denominator, and we can compare the result. If for some reason we're still getting an indeterminate form, then we can take the second derivative separately of the numerator and denominator, and we can complete this process as long as we can differentiate until we get a result for the limit. So the reason this works is now that we know that derivatives are rates of change, if you get a 0 over 0, for example, well, if I have an exponential over a polynomial, well, that exponential, if it's reducing, is going to get to 0 faster than a polynomial will. If we have infinity over infinity, the numerator or denominator might be growing, right, faster than the other part of the equation. So what the derivative does for us is it allows us to, one, simplify the equation down, because a lot of these problems the derivative will actually get simpler. Second of all, though, what you're doing is you're comparing the rate of change of the numerator to the rate of change of the denominator, or another way to think about it, you're comparing the speeds. And eventually, when you start comparing the speed, and then if you were to do the second derivative, essentially it's the acceleration, right? And then the third derivative would be the jerk function, right? So if you kind of think of it almost like in a physics context, you're getting the rates down to where they're distinguishable. And then you're trying to decide, well, does the denominator win? Does the numerator win? Or are they approaching those values at a ratio of two numbers that we can actually quantify and measure? So one thing that you want to make sure that you don't get confused is this is not the quotient rule. The quotient is how you take the derivative of the entire expression. We're just comparing the rates of change of the numerator to the rates of change of the denominator, and this is only true of the limit. So sometimes when people are working in a hurry, they may mix these two rules up. We can also apply L'Hopital's rule to one-sided limits as long as these functions are differentiable around the edge of this domain. So with infinity, right, you're kind of on the edge of things, so it really only needs to be differentiable on the one side, but we could have changed this to an a from the right, a from the left, as long as it was differentiable from that direction on the function. If for some reason your limit is not 0 over 0 or some combination of infinity over infinity, you cannot use L'Hopital's rule. So if you're in a situation where you have 0 over a constant, right, we can't apply this. So there are some other indeterminate forms where we may be able to apply L'Hopital's rule. So the first thing we have to make sure that we do is we verify, right? So we did the same thing back in Unit B when we were doing limits. Before we started algebraically manipulate it, we said we never set the limits equal to these, but maybe off to the side we would verify that that's why we were moving ahead with our algebra. So the indeterminate forms are, these are the two that you can immediately apply L'Hopital for. However, you could have an indeterminate difference, right? We could also have 0 times infinity, right? And we're not really sure what the limit of that is, right? Which one of these wins? You could have an indeterminate power, so 0 raised to a 0 power, or 1 raised to a 0 power, or infinity raised to a 0 power. So some of these forms, there may be ways to algebraically manipulate the expression you're looking at to turn it into an actual ratio of two expressions and look at it. So the indeterminate difference, try to combine the function using a common denominator if possible. So only if they have common denominators. But just because you're getting these guys doesn't mean you can just arbitrarily take derivatives. If you have indeterminate products, so that would be something like this, well then one way we might be able to get around it is we might be able to move one of these expressions into the denominator. So keep in mind here, this is not an inverse. Okay, these are not inverse functions. This is we're raising it to the -1 because we're moving it into the denominator. We're going to see examples of all of these things played out in today's lesson. The third is indeterminate powers. With an indeterminate power, just like when we learned we could take the derivative of like x to the x by using the properties of natural log, well, if we have an expression of x being raised to an expression of x, we can actually use logs in a very similar fashion and reevaluate the limit. When you get down to the result of the limit, the left side of the equation is still natural log of y. So just like we did with the derivative, we'll have to solve for y by raising both sides over e. So this is a lot to take in at the beginning of this, but that's okay. It's here for you really to review back on when you're working on problems on your own, but we're actually going to see all of these things demonstrated in tonight's guided exercises.